Hello and welcome to this talk on benchmarking elasticity of FaaS platforms as a foundation for object-driven design of serverless applications. This work has been written by Jörn, Kuhlenkamp, Maria Borges, Dominik, Ernst, Daniel Wenzel, and me, Sebastian, Werner, and we are from the Information Systems Engineering Group at TU Berlin. In this work, we benchmark the elasticity of FaaS platforms, and that this is important can also be seen in recent use. As you can see here by this news article, there were reports that the cloud is full. In particular, users of the UK region of Microsoft Azure Cloud reported that they could no longer start new VMs, and in particular could no longer start serverless workloads due to a resource issue, which is weird because developers think that cloud resources are unlimited. In this case, they were not, which is also why it's important to do continuous benchmarking and measurements to see how cloud platforms behave under different workloads. In fact, during our experimentation, in this case, we also saw that Azure has some difficulties with volatile workloads. To begin with, however, I'm going to give you a brief background into FaaS platforms. Function as a service is a relatively new paradigm in cloud computing, and many platforms already exist, both commercial and open source. For example, IBM Cloud Functions or Amazon Lambda are commercial solutions, but there are also open source solutions like OpenWhisk or Knative. Currently, some applications are already using FaaS, mostly async processing and non-real-time web serving use cases. Because it's not trivial to use FaaS for all possible application scenarios, however, industry and research are specifically focusing on application scenarios such as real-time web serving, explanatory data analysis, and periodic batch processing as possible use cases for FaaS. These function as a service platforms are always based on an event-based programming model, which means that the developer only defines the functions in terms of code and triggers for that functions. Triggers can be HTTP requests, carry events, or storage events, and also other cloud provider events. These functions then usually live within this ecosystem of one cloud provider, generating new cloud events or new HTTP events, or calling other FaaS functions. The value proposition of this is that FaaS offers a fine, granular execution-based billing model, meaning that developers only pay for resources that are actually used to service the events. This also, however, means that resources are only provisioned if events occur. Furthermore, FaaS platforms offer provider-side managed operational tasks, meaning that you as a developer no longer have to manage load balancers, updating environments, patching VMs, and so on. This is all done by the provider. And lastly, and most interesting for this work, FaaS platforms offer a workload-driven elastic autoscaling, meaning that the provider decides how to respond to an increase in load, and you as a developer don't need to care about this anymore. We focused on this elasticity of FaaS platforms, specifically the ability of FaaS platforms to process arbitrary numbers of incoming events. This enables developers to defer throughput decisions as much as possible to the cloud provider. For example, it's really hard to design real-time web serving that is capable to handle rapid interest due to a viral social media event. But it's supposedly free with FaaS, and that's what we wanted to look into. Specifically in this work, we asked the research question: does the quality of a FaaS platform change from a client-side perspective under volatile workloads? And is this change relevant in an application context? Specifically, we present in the paper an experiment design and evaluation of 4 FaaS platforms and an applicability analysis of 3 application scenarios on these platforms. In this talk, we will cover the experiment design and an excerpt of our evaluation. For the rest, we invite you to read the paper. In some sections, we highlight things that we had to leave out of this talk with this red arrow that might be of interest to you, and there's additional information always available in the paper. In order to visualize our question a little bit more clearly, I want to show you this graphic here. as you can see, we are interested in the quality of these platforms under volatile workloads. Specifically for these platforms, how is the client-side latency effective during a volatile workload change? And also, what other side effects can be observed from the client side, such as failures or cost impacts? For that, we created a design of an experiment consisting on a design based on the Cloud Service Benchmarking book by Bernbach et al. A design starts out with a workload generator that sends HTTP-based traffic to a deployed function in the system under test. I'm going to about the different workloads we used and the design of the workload in general later on in this talk. We further designed a set of measurement points that we included in the function we deployed to obtain all the information we were interested in. So we could later analyze them, extract the metrics, and present the results to you here and in the paper. In total, we had 5 different workloads on 4 different platforms. And if you're more interested in the tool or design of the experiment, I invite you to read again the paper and look at our tooling on GitHub. In total, we applied our experiment to 4 providers, namely Amazon Web Services Lambda, Google Cloud Functions, IBM Cloud Functions, and Microsoft Azure Functions. On all of these platforms, we deployed a function with 1 GB of memory using a web trigger in a Node.js environment. The function we used to evaluate these platforms was a prime number validation that took always 2 seconds, or around about 2 seconds, with the given 1 GB of memory. On all of these platforms, we then ran different workloads. For our experiment design, we defined a generic workload model. This model consists of 3 phases: a warm-up phase of 60 seconds, a scaling phase, also of 60 seconds, and a cool-down phase. In the warm-up phase, we tested the cold and warm start behavior of these functions by either providing a fixed workload or not. In the scaling phase, we always ramped up the workload to a specific target. In the cool-down phase, we kept that workload stable to see how long it would take the platform to normalize. In the rest of the presentation, we are only going to discuss the workload you're seeing here right now, which is workload 2. Workload 2 is our most extreme example, including a cold start with a volatile increase in requests up to 120 requests per second. If you're interested in the other workloads we used, I invite you to look into the paper where we describe the other 4 in detail. At multiple measurement points, as I showed you in the beginning, we were interested in different client-side qualities. Specifically, we are interested in cost, latency, and failures. Failures are obviously easy to measure. We just observe if the client sees anything. If a request doesn't come back, that means it failed in some way. If we get back a failure code, we can also record this. For the request response latency, we simply measured the time we started to send the request, represented by 1, and the time we received the response for this request, represented by 4. The time in between is the time it took the FaaS platform to execute our request. But we could do even better, because the second our function receives a request, we can mark down this timestamp, and the second we send it back, we can mark down that timestamp as well, giving us the ability to also measure the execution time, the real execution time of our function. The time between 1 and 2 is the time it took the FaaS platform to deploy the function, to route something, to do scheduling, and so on. And we defer to this time in the paper as provider latency. And we were also interested if this changed during volatile workloads, of course. We also employed a number of other measurements. Specifically, we tried to fingerprint the host and runtime environment to find out how many hosts were used to process our workload, how many functions were deployed. We also checked the cold and warm state of a function, all that to get more detailed information. Based on these measurements, we extracted multiple metrics. Among them, the most important request-response latency, cost, and reliability. Request-response latency could be extracted directly from our measurements, while cost would be extrapolated based on the execution latency. Because FaaS providers bill you based on the execution time or execution latency of your function and the provisioned memory you used, in our case 1 gigabyte of memory, and based on that we can calculate the cost. Lastly, failures, we use the ratio of failures to extract reliability of these different providers. For each metrics, we plotted them as shown here, either in these 99 percentile graphs over time or in failures and requests over time. For each of these metrics, we created a visualization for all workloads on all providers that is available on our toolkit in GitHub, and we also have examples of this in the paper. I'm now going to show you one of those examples of our results for Workload 2. What we can see here is a comparison of AWS Lambda and Google Cloud Functions. The first thing that we noticed when we looked into the data here is that the execution latency in both cases is about the same. However, this is a totally different story on the client side. As you can see in Google Cloud Functions, the mean request-response latency increases during the increase in workload. What you can also see is some peaks in the 99 percentile where the latency goes over even 30 seconds. And also we see some peaks during the cooldown phase. Also, we see some failures here where Google Cloud Function was not able to respond to some of our requests. These failures were mostly timeouts. What you need to know here is that the timeout for web triggers is per default 30 seconds. We wanted to understand what is happening here, and therefore went a little deeper into the data, which is what I'm going to present to you now. What you can see here is our provider view. What we show here in blue are newly created execution environments, meaning that that's the first time we see a new execution environment during our experiment. The red dots you can see here also show that an event is processed by this particular runtime. The darker these dots, the more events were processed by that runtime in this time period. The first thing that we noticed looking into the data is that Amazon created a lot more runtime instances than Google Functions. Second thing you might notice is that Amazon only created new instances during the change in target throughput, while Google was lagging behind, which might be one reason why we see this increased mean response latency. Another thing you see in Google is that the workload between different runtime environments is not equal, meaning that there also might be some issues and some failures explained by that. A more detailed description about these plots and also the other runtime environments and providers you can find in the paper. Based on the presented and other results in the paper, we can see significant difference in these FaaS platforms under volatile workloads. These platforms seem to make different trade-offs to deal with volatile workloads. However, Amazon and Google both show the best elasticity with different side effects. Amazon was overall the most mature platform here. However, we think that a careful evaluation of FaaS platforms according to application scenario requirements should be done when you want to deploy on any of these platforms. And we also think that you need to reevaluate these platforms using our toolkit periodically to see if something changed, because these platforms are under rapid development. Because as you can see here from the table, Microsoft Azure Functions had a really high failure rate, and we believe that that's basically because they started a little bit later with function as a service and might not have implemented the same strategies as all the others. In conclusion, we saw that FaaS platforms differ in elasticity, and we provided an experiment design and toolkit to, first of all, measure this, and also to continually evaluate your platform choices. Also, we recommend that you choose the right platform for your specific application scenario. If you're interested in the topic of FaaS, in the topic of serverless, we have also other projects going on our chair. For one, a project about migration of data processing to serverless systems. And also upcoming is a paper and presentation in 2-3 weeks at IC2E, where we synthesized our research of the last 3 years in the field, called the ifs and buts of less and more, a serverless computing reality check. If you're also researching in this field, we also created a serverless knowledge base containing literature and experiments in the serverless ecosystem that you can look here if you're interested. Thanks for your attention, and that's all from me.